Welcome to Lecture 5 of CS 159, the Advanced Topics in Machine Learning at Caltech. This term, the advanced topic, is data-driven algorithm design. Data-driven algorithm design has many connections to reinforcement learning and imitation learning. And today we'll be providing an overview of both reinforcement learning and imitation learning and talk about their connections to learning to optimize, including many of the settings that we've already seen in previous lectures. I should mention that much of the material in today's lecture is based off of two sources. The first one is a short reinforcement learning course taught by David Silver, who was a lecturer at University College London and is now a researcher at Google DeepMind. For those of you who don't know, David Silver was one of the leading people who designed AlphaGo for DeepMind. That beat the Go world champion. This material is also based off of a tutorial that myself and a former PhD student of mine taught on imitation learning at the International Conference for Machine Learning in 2018. Both of the primary sources of that this lecture is based off of are available in the link below, and of course the slides to this lecture are available on the course website. Okay, so ingredients for learning. Let's just open these. So there's 4 ingredients to learning for reinforcement learning and imitation learning. You need an environment, you need a policy class, you need some sort of loss function or objective function to characterize how well you're doing. And you need an algorithm that, given these pieces, can then learn a policy that optimizes your loss function or reward function when rolled out in your environment. When we're doing reinforcement learning, the loss function or reward function is derived directly from the environment. Like, for example, if you're playing a game, it could be whether you win or lose the game or number of points or something along those lines. These are things that you can directly measure from the environment for various states and actions that you do while interacting in the environment. In imitation learning, the loss function is derived from expert demonstrations. So someone, an expert of some kind, has demonstrated what to do in this environment, and you're given a collection of those demonstrations, possibly direct access to a teacher, but in the simpler case, just a collection of demonstrations, and your job is to basically learn to imitate the behavior of the expert. So in this particular state, the expert did action A, so I should design a loss function such that the policy class, such that the learned policy prefers to do action A over the other actions. So that's the basic idea. Given that backdrop, so reinforcement learning in a nutshell is, given an environment slash simulator, we sort of use the two terms interchangeably, at least in the simpler settings of reinforcement learning. The goal is to design a policy that can sample trajectories or state action pairs from the simulator, and through those samples, estimate high reward actions. And we'll get into some more details of that in a few slides, but that's reinforcement learning in a nutshell. So you have this environment, which in this example below is a game, is a race car game, and we have states here represented by these game screens. So the features are derived from these images in this particular example. And we have actions like how to turn the steering wheel. And in certain states, keeping the steering wheel angle straight will give us high reward because we keep accelerating, we're going fast, and that can be measured as high reward. In other states where the road is turning, keeping the steering wheel angle straight will result in low reward because we'll fall off the racetrack. And so this is from interacting with the environment, we can collect these data points. So in this state, taking this action gives you high reward. In this state, taking this action gives you low reward. And that's the training data for learning. And from that, we apply we convert that to a loss function for learning. That's the basic idea. One thing to note is that the policy or the agent is doing both the data collection and the learning. So the learning algorithm is both figuring out how to collect the data and how to learn from the data that it collected from itself. whereas in supervised learning, the data is given to you exogenously, typically assumed to be sampled IID from some generating distribution that is outside of the control of the agent. Sorry, skipped one slide. Imitation learning in a nutshell. So in imitation learning, we are assumed that we're given demonstrations or access to a demonstrator. Sometimes we assume access to the simulator, although it's not strictly speaking necessary for all forms of imitation learning. And then the goal is to train a policy to mimic the demonstrations. So you have these expert demonstrations of, in each state, what action the expert did. And then this gets converted to a loss function, very similar to supervised learning, where the policy says you want the policy to say, in this particular state, I want to keep the steering wheel straight. In this other state, I want to keep the steering wheel turned right, because that's what the expert did. And we can define a loss function that characterizes the mismatch between what the policy predicts at any given state versus what the expert demonstrations actually did. And so here, you may have access to the simulator, but you definitely have access to demonstrators that tell you what the correct action is for a given state. And so the sampling of the correct actions is typically given to you by a demonstrator, and you don't have to sample for it yourself. Oops. Sorry about that. So a little bit of notation. This is fairly standard notation, although you may see some variations in various papers or resources. And sometimes because I'm drawing material from multiple different papers in these lectures, sometimes the notations vary a little bit as well. But this is a very, very standard version of the notation. So we have a state. It's typically noted S. Sometimes it's noted X. The state may only be partially observed, which means you may not observe the full game state. So for example, in these video games, you typically only observe what you see on the screen, which is not actually the full game state. You have an action, typically noted A, occasionally denoted Y, and you have a policy, typically noted pi, sometimes noted H. We certainly used H a few times in the earlier lectures. A policy maps states to actions, so it takes as input a state and it outputs an action. Theta is the subscript theta refers to the parameterization of pi. So if pi was a neural net, then theta would be all the parameters of the neural net. Oftentimes, pi is stochastic, or it's a stochastic policy, which means it maps states to distributions of actions. So now pi sub theta of S maps to a distribution over possible actions, and then when we actually take an action, we sample from this distribution at this state. We have a dynamics or a transition function, which is given a current state, given the action taken in this state, what is the next state? So if I'm in a particular place on the racetrack and I decide to turn right, where am I in the next time step? The dynamics is typically not known to the policy, and this dynamics is basically the environment of the simulator. So if you knew exactly this transition or dynamics function, then you would exactly know what the environment is doing. A rollout is when you sequentially execute a policy starting from some initial state, and you produce a trajectory of state action pair sequences. So tau in the first bullet point is the rollout trajectory. It's the trajectory obtained from rolling out pi from state S naught, and it's just the sequence of state action pairs. Sometimes I should note that this trajectory also includes the reward. So you get a state, you get an action, you get the reward you got in that state, and so forth. So the trajectory rollouts can also include rewards that we obtain for each state action pair. We can talk about, and this is just the next two notation is just for notational convenience. We could talk about the distribution of trajectories induced by a policy, which is basically, you do a rollout and then you look at, the distribution over trajectories. We could talk about the induced distribution of states. by a policy, which is just the probability that a policy will visit a state at any point in time in the rollout. So it's averaged over time. And then we have some sort of reward function. The reward function in this notation is typically used only in reinforcement learning, because it's in reinforcement learning, it's often phrased as a maximization problem of reward rather than minimization problem of cost. Although many reinforcement learning problems also frame it as a minimization problem over cost, but they're just sort of opposites of each other. And in this case, the reward is specified in a state action pair. So in this state, if I get this action, if I take this action, it gets this reward. If it's directly from the environment, the actual function is not known to the policy, but you can sample the reward by executing this state action pair and observing the measured reward from the environment. So if I'm in a game, I'm in this state, I take this action, I win, then that's the reward I measure. And then the final thing is the value of a policy. So it's basically saying, what is the expected value of the rollouts of a policy? Oftentimes in reinforcement learning, there's a discount factor. That's what gamma is. It's a number that's strictly greater than 0. Actually, I should rephrase. It's between 0 and 1. It's not strictly great. It's not necessarily strictly greater than 0. It can be 0. And it basically measured how much this policy cares about the future. When you're modeling reward, how much do you care about the future? And the future in this case is discounted geometrically as we go further and further into the future. And the expectation is over the randomness of the decision making of the policy and the randomness from the environment, such as their transition function. So that's the basic notation. Any questions thus far? Okay, so we can also take an optimization perspective, and we'll look at optimization perspectives quite a bit in this lecture, because in some sense those are the nuts and bolts of reinforcement learning and imitation learning. So you have your policy or agent, that's pi. It's taking actions and interacting with the environment. In this case, it's getting back new states. Sometimes, and you can also measure some sort of loss function or reward function. In reinforcement learning, the reward is sampled directly from taking this state and action, taking this action in this state in the environment. In imitation learning, you get some sort of imitation loss that's derived from demonstrations from some sort of demonstrator or expert. Right. So in reinforcement learning, you only measure that at time at that specific state action pair. One thing that's kind of interesting is that oftentimes, although not always, in imitation learning, the loss function is fully specified at a state. So if the demonstrator said, at this state you should take this action, then if that's the only signal you have for learning, because you're not, in this case, you're not actually even measuring reward from the environment, then it's basically like a classification problem. At this state, there's one correct answer and there's a bunch of incorrect answers. So it's like a multi-class classification problem, which means that you have this fully specified loss function for this state. You know what the right answer is, you know what the wrong, and everything else is the wrong answer. Whereas in reinforcement learning, you'll notice that you only sample the reward of the action you took at that state. You don't know what reward you would have gotten if had you taken a different action at that state. So in some sense, you only get partial measurements of the reward function or the objective function, whereas in imitation learning, you get a more complete measurement of the objective function per state. And I'll come back to this issue when I talk about the exploration-exploitation trade-off. But this is a fairly important point to make. Any questions about this at a conceptual level? Okay. So again, I'm going to write reinforcement learning here as a maximization problem over rewards. But you could also write it as a minimization problem over costs. It's just the two are essentially equivalent. Just how you decide to formulate the problem. You get in this particular way I'm writing it, and I'm going to write it a few different ways in this lecture. In this particular way, I'm writing it as the induced state distribution induced by the policy. That's what the expectation is taken over, and by the dynamics of the environment, and then what is the expected reward we get, and find the policy that maximizes it. And in imitation learning, in this particular way of framing it, the two objectives look basically the same. The key difference is that we're now minimizing a loss function where the correct answer is whatever the demonstrator is doing. That's what A star of S is in the learning objective for imitation learning. That's the demonstrator. And again, note that the expectation of the state distribution is induced at least partially by our policy pi, whereas in normal supervised learning that we covered in CS 155, the expectation is the distribution of the data is exogenously given to us. So suppose the policy is suboptimal, then reinforcement learning only knows that the specific trajectory that it executed in the rollout has low reward. It must sample more from the environment with more trajectories in order to find a trajectory with higher reward. And this is known as exploration, because it doesn't know what the right answer is, and it must try random things in some sense and measure the reward to know what is the best thing to do. And it has to balance that between trying things that seem completely random, but might be good, but we don't know because we've never measured it, versus fine tuning or zero in on state action pairs that seem good, and just like tuning the actions to get slightly higher reward in the area of the state space that it's already explored well. That's the exploration-exploitation trade-off. It's essentially the same trade-off that we saw in Bayesian optimization, but now there's states involved. So in Bayesian optimization, you take a single action and your rollout is over. So Bayesian optimization and bandits are basically simplifications of reinforcement learning, where the time or the length of the rollout is 1. Whereas in reinforcement learning, the length of the rollout is much longer than 1. So it's actually a much harder exploration problem. In imitation learning, assuming you have access to an expert who can tell you what's the best thing to do, then the expert basically says, at this state, this is the best thing you could have done, which again translates to a fully specified loss function at every state that you're collecting data for. This is just another way of revisiting the same issue that we've been talking about the last few slides. But this is a very important concept, and so it's worth spending a few slides looking at it from a few different perspectives. So when to use imitation learning versus reinforcement learning. Obviously, when expert demonstrations are available and reliable, you should use imitation learning. When the environmental reward is hard to specify, like you don't even know what a good reward function is, then maybe you want to invest time to collect expert demonstrations, even if they're not readily available. Or if the environmental reward is super hard to optimize, like it's very sparse. For example, although we've since now solved this problem, at least Google DeepMind has, in the game of Go, the reward function is, did you win or lose the game? which is super sparse in terms of the landscape over state action pairs. It's 0 most of the time. It's +1 when you win the game. It's -1 when you lose the game. One should use reinforcement learning when experts are unavailable or unreliable or highly suboptimal, when there's a reward function that is readily available or easy to specify and relatively easy to optimize. For example, it's dense in the state action space rather than sparse. And of course, there are many interesting research questions about how to blend imitation learning and reinforcement learning, and we'll talk about some of those. We'll touch on some of those later on in this lecture, and we'll have another lecture that touches on them in more detail. So this is just to sort of paint the picture of how we get between imitation learning and reinforcement learning from standard supervised learning from a optimization technique standpoint. So what type of optimization techniques under the hood do we need to solve these types of problems? So on the left we have conventional supervised learning, the thing that we covered for over half of CS 155, or about half of CS 155. If the decision-making predictor or policy, as we call it in this lecture, is executed sequentially over states, then we can, to a first order approximation, think of that as the optimization problem that we need to solve for imitation learning. That's the bottom track. On the top track, we have online learning. So we're collecting data on the fly. We don't have this ability to for someone to tell us what to do. We're collecting data on the fly, and we don't observe all the rewards for all the state action pairs, and so that's what partial feedback means. And so we get to bandits when we have partial feedback on the fly learning or partial feedback online learning, where we only observe the reward of the actions that we took. Now, bandits and Bayesian optimization are stateless in the sense that that basically, for the purposes of optimization, means that the time horizon of the rollout is 1, has length 1. And if you want to maintain states, then that essentially means, at least in this somewhat simplified depiction of the landscape, that means you have rollouts of time horizon greater than 1, and that's how you get to reinforcement learning. And on the bottom arrow, if you go to partial feedback, where you don't know what the right answer is, you only know how good the action you took at your current state, then at least from an optimization perspective, in terms of the mathematical tools we need to solve the underlying optimization problem, you get from the difficulty of imitation learning to reinforcement learning. Any questions on this? Yes, question.
Are there clever ways to navigate the exploration and exploitation trade-off that don't rely on Bayesian optimization?
Thank you for the question. Clever is in the eye of the beholder. I think we're going to cover a few methods later, just in a few slides, actually. They're not particularly clever in the sense that they seem. Let me backtrack slightly. Clever is in the eye of the beholder. The methods that we'll cover today will seem pretty basic or simple. Nonetheless, I think they are clever in the sense that if you make your method too complicated, then it's harder to understand when it works and when it doesn't work. So we're going to cover some very basic methods that are known to be good starting points for exploration. And then if you have more domain knowledge, you can build upon those methods to get a method that's more efficient for your particular application. And these methods are not Bayesian optimization methods, although they are closely related. So the outline today, we're going to go over some basic reinforcement learning algorithms, go over some basic imitation learning algorithms, and we'll look at how to map that to learning to optimize problems that we've already seen in lecture. Okay, so reinforcement learning. We're going to go back to this reward function formulation that I had before with this discount factor. If the discount factor is 1, then it's not discounted over time. If the discount factor is exactly 0, under the assumption that 0 raised to the power of 0 equals 1, I only look at the current time step, and I ignore the reward and future time steps completely. One important notation that I'm going to add right now that's very important for reinforcement learning, somewhat less important for imitation learning, so I didn't add it earlier in the notation, is this notion of a Q function. A Q function is specified by a policy pi, that's the superscript, and it takes as input a state action pair, and it represents the reward function of taking an action A at that state S, and then following policy pi into the future. In other words, what is the reward we expect to get if we take action A in state S and then follow pi after that? If action A is actually the action taken by pi, then so Q superscript pi of S comma pi of S is exactly the reward function or the total value function of the policy, and you see that in the third line. Some people talk about the Q function as a one-step deviation. So we're going to take a one-step deviation from policy pi, and the deviation is we're going to instead take action A at this state instead of whatever action pi would have taken, but then we'll follow pi for the rest of the time. This is an important concept because it's used in all the optimization and learning algorithms that we're going to cover for reinforcement learning in this lecture, this Q function. Sorry. Okay, so we're going to talk. We're going to restrict ourselves in the context of reinforcement learning to only stochastic policies, and the reason for that will become clear in a few slides. Excuse me. So if we have a stochastic policy, then we can write pi of SA as the probability that the policy chooses action A at state S. So this is a slight abuse of notation. So pi of S is the decision of the policy, and pi of SA for stochastic policies is the probability of choosing action A at state S. And this notation is very common when talking about stochastic policies. So in order to do learning, differentiable learning, we need to be able to take gradients and apply chain rule and all that stuff. And so this is one thing that's often used in gradient-based learning for reinforcement learning, which is the so-called score function for stochastic policies. And it's motivated by this particular derivation. So you take if you want to take the gradient of a policy, the first equality is just multiplying and dividing by the probability of the policy. So you multiply for a given state action pair, you multiply by the probability of taking that action in that state, and then you divide by the probability of taking that action in that state. That's all that the first line is doing. It's just multiplying and dividing by the same number. But then you observe, okay, if we group the second two terms, if we group them together, that's actually the gradient of the log of the policy. So we can write the gradient of the policy as equal to the probability distribution, probability weight of the policy for that state action pair times the gradient of the log of the policy for that state action pair. And this will become very convenient notational derivation when we talk about gradient-based learning. Right, so we're going to use this, and we're going to apply, apply chain rule to basically optimize the value function given stochastic samples from this expectation. So we're not going to be able to, of course, integrate over this expectation. We have to sample trajectories to approximate this expectation empirically. Let's go over two very common stochastic policy classes. The first one is a softmax policy, which is very common and popular for discrete actions. And in the first line, you see that the probability of taking an action in a state is proportional to the exponential raised to some feature map transpose theta, where theta is the parameters of the policy. And the score function is in the second line. And if you recall from what gradients look like for logistic regression, this looks a lot like the formulation of gradients for logistic regression, and indeed there's a really close connection here. And again, for deep learning, this feature map phi is also learned. So this is the formulation that we would write for linear softmax policies, where you handcraft the feature map. And for deep learning, phi is also learned, and then theta would just be the weights on the last layer of the neural net, and phi would capture all the weights up until the very top layer of the neural net. And indeed, for most of the straightforward ways of doing deep reinforcement learning, we start with the linear policy that looks like this, and then we just allow phi to also be learned, and it's specified by some neural architecture that you think is useful for this particular problem, and that's how you get deep reinforcement learning. This is part of the reason why many reinforcement learning experts in the field, they don't think of deep reinforcement learning necessarily as its own field, because most of the action happens at this level of formulation, and the only thing that switches from reinforcement learning to deep reinforcement learning is that this phi function is also learned, and you just apply chain rule. Other experts in the field disagree. They think that deep reinforcement learning is its own field. And so you'll see this disagreement sometimes if you sort of read papers or see talks by other experts in the field. I'll leave my own opinion out of it for now. Another popular policy class is the Gaussian policy. This is very common for continuous actions. So for any given state, we have a so-called mean action. So that's the first line. And the mean action, or the average action, if you will, is just some feature mapping of the state and plus a linear inner product with the parameter vector. And a Gaussian policy is specified in the second line, is basically for any given state action pair, the action is sampled or is specified according to a Gaussian distribution with mean equal to the mean action and some variance term. For more advanced formulations of this policy class, the variance can also be learned as a function of some other theta vector. But in this particular simple case, we're just parameterizing the mean function, the mean action, not the variance of the actions. And so if the action distribution given a state is Gaussian distributed like this, then the score function, that's the third line, takes the following form. And again, for deep learning, the phi function is also learned, and therefore the theta vector, it can be thought of as the weights of the top layer of the neural net. Any questions so far? Oops. Okay, so this is one of the most important results in reinforcement learning. This is the policy gradient theorem. And I'm writing it in a more informal way because there are restrictions that apply to the form of J and Q. So this theorem doesn't apply for all possible J and Q. But I'm going to sort of ignore those conditions for now. If you're interested, you could I refer you back to David Silver's lectures, linked to at the beginning of these slides. But this is the statement of the policy gradient theorem, which is if I want to take a gradient of this policy with respect to the parameters of the policy of the objective function, then it is equivalent to the following, which is you take the expectation over state action pairs encountered by pi. So you roll out this current pi in the environment, the expectations over the randomness of the state of the dynamics or the transition functions of the environment, and over the choices of pi. And it's equal to the gradient of this, equal to the score function times the Q function. And something that's really nice is that, you know, this moves the gradient, this form is basically the form that enables us to design gradient-based learning of policies, and then we can think about how to make it then more efficient. So we can directly optimize this via stochastic gradients. And we've seen this algorithm before, and I'll just present it again. I took the version that was presented in David Silver's lectures. So this is just a screenshot of his lecture notes. The reinforced algorithm is the simplest reinforcement learning algorithm. It is a policy gradient algorithm. And the key thing that it's doing, let me go back to the policy gradient theorem, is that if you want to optimize this objective function, basically what you do is you roll out pi a few times to get an empirical sample of this expectation. And then you compute the score function and you compute the Q function, or you compute the score, the score function, you compute a value of the Q function or an estimate of the Q function. And then you differentiate the theta in the score function, and that's how you update your policy. So that means we need to estimate the gradient of the score, which is the score function, and then we need to estimate that Q function. And what reinforce does is it basically just does this unbiased Monte Carlo estimate of this Q function. That's the line that's being highlighted with the arrow. So that V sub t is just looking at the trajectory rollout that of the policy, and then just using that as a single Monte Carlo estimate of the Q value. And this, you can show that this is actually an unbiased estimate of the gradient. And so this is a valid stochastic gradient descent approach for reinforcement learning. Such methods are known as policy gradient methods because they're doing gradient descent on the policy directly. And the reinforce is arguably the simplest possible policy gradient method. Any questions? So the benefits, it's simple, it's an unbiased estimate. The drawbacks, very high variance in practice, especially for long time horizons. This Q function, this Q value, you have to recall that it's defined recursively over the entire length of the trajectory. So it's the Q value. Let me just go back to the definition of the Q value, which is right here. It's defined over the length of the trajectory. So if you want to compute, if you want to have an unbiased estimate of this, you have to roll out the entire trajectory to get an unbiased estimate of this Q value. Because you have to take this sequence of nested samples or nested expectations. What that means is that this Monte Carlo estimate basically by taking this single sample of the Q value has extremely high variance, especially for long time horizons. This is something that does not arise in Bayesian optimization and bandits, which are stateless. This is the key difficulty, one of the key difficulties. And so you have some options. You could take many stochastic samples. You take many samples before you take a gradient step. or you take very, very small gradient steps because your estimates are so noisy. So you set alpha, the alpha parameter here in the gradient, the step size to be very, very small. Either way, that means the learning is very slow because you have to do rollouts, a lot of rollouts of the environment in order to get this gradient estimate, which can be very slow. Any questions about that? So the main class of approaches that people take to combat the high variance of this Monte Carlo estimate of the Q value is called actor critic. And the idea behind actor critic is you estimate the Q function over a parametric family. So rather than doing Monte Carlo estimates of the Q value, we're going to learn a model of the Q value or estimate a Q function and have that be parameterized in these days with a neural net. So again, this is just a simple algorithm. Probably the simplest actor critic algorithm. Again, this is just a screenshot from David Silver's lecture notes. And the key thing is that I want you to pay attention to, it's not important to look at the entire algorithm. The key thing is that we learn this Q estimate as a parametric model. So what that means is that this is now no longer an unbiased estimate, or typically not an unbiased estimate of the true Q value, but it has much, much lower variance. So we get this bias variance trade-off that happens in this particular case. And then the next line is the standard policy gradient step that we saw in the previous slide as well. But now, instead of taking this Monte Carlo estimate of the Q value at each state action pair, we take the prediction of this model that we're learning. This model of the Q value. Any questions? Okay, so there are many other policy gradient-based methods that look at other issues that arise, such as how large do you set the step size, how do you do sampling, how do you get more sophisticated actor critic methods that have even better bias variance trade-offs, and many others as well. Here is just a sampling of some of the more popular ones that people use these days that are fairly compatible with applying chain rule, I guess, for deep reinforcement learning, and there are many others. But I think these, the methods listed here are basically enough to get anyone started if they're interested in doing reinforcement learning for either their blog post or their final project. The other method that I will briefly mention, first let me talk about exploration. This was also asked before, and then I'll talk about one more method very briefly. I want to talk about exploration. So we talked a lot in this lecture about how we need to sample from the environment to collect data in order to find states and actions that have high reward, and that is the learning signal. So we're going to come back to the fact that this expectation in this reward function depends on pi. It depends on the actions taken by the policy to get the sequence of states. What that means in practice is that you need a non-zero probability of sampling every state. You cannot have a policy that that takes actions in such a deterministic way that some states, parts of the state space that have high reward are never sampled or never explored. And so some people actually think about ways of making pi more random in the beginning and then less random later on. But that's something that you have to keep in mind. So I'm going to close the section on reinforcement learning with one more class of algorithms called Q-learning. And what Q-learning does is, again, it looks at this Q function, and it says, what if we can learn this Q function well enough that it can be used for decision-making directly? And so that's what the first line is. Suppose we have this parametric model that estimates the Q value. And suppose that we've learned it well enough that we can directly use it for decision making. And so given a current state, the action we take is just the action that maximizes the our Q value estimate or Q function estimate at that state. And so the basic Q learning algorithm is specified below. So we have this, during training, we have this policy that does exploration. I'll call that pi prime. That's the first bullet point. And what pi prime does is it takes the action of pi with probability 1 minus epsilon, and it takes a random action, a completely random action with probability epsilon. And then we roll out pi prime, and to collect state action reward tuples. We fit the Q function on the data we've collected, and then we repeat. So this is Q learning, or the basic version of Q learning. And here, the randomness, again, we talked about how we need to have enough randomness in the policy that we can potentially explore every state action pair. This type of randomness is called epsilon greedy exploration. In policy gradient methods, the exploration is based on what the policy thinks is likely or more likely or less likely to have high reward. The policy is stochastic. It's going to and it's trained in a way such that high reward states it's more likely to explore high reward states or states that it thinks are high reward, and less likely to explore states that I think are low reward. Whereas in Q learning, when it does exploration, it just does something completely random. So policy gradient versus Q learning. Policy gradient is more general, but typically has much higher variance during learning. The Q function may be hard to learn well enough for decision making. In policy gradient, at least in active critic, the Q function is learned only to weight the gradient on the policy itself, rather than using a Monte Carlo estimate of the Q value. But in Q learning, the Q function has to be learned well enough to be directly used for decision making. Both methods have demonstrated strong performance depending on which regime you're in, and you can refer to some of the references to sort of get a bigger picture of that. And there are other approaches that we're not going to cover, but they're important in other contexts, but they're less relevant. Except for the last one, bridging reinforced learning and imitation learning in the context of learning to optimize. Any questions? So now we're going to move on to imitation learning. I think in the interest of time, I'm running a little bit behind schedule. I'm going to skip this slide. This is just a video of the first application of imitation learning in self-driving cars. From the early 1990s. If you have time, I encourage you to watch this video. But let's just move straight into the example. So we're going to use this race car game as an example. So the state is the game screen, and the action is the turning angle, and then we have this set of demonstrations given to us by an expert. So someone's playing this game, we're recording this person's actions as they're playing the game, and we have this sequence of demonstrations of state action pairs. We want to learn a policy that imitates this state action pair. Something that I do a lot of work on in my personal research is imitation learning for sports analytics. So here the state action pairs correspond to locations of the players, and the ball and the action are the next locations of the players at the next time step. And we again get the sequence of state action pairs when we want to build policies that imitate the behavior of, in this case, professional basketball players from the National Basketball Association. And there are many data sources. So in imitation learning, you need access not just to a simulator, but the ability to collect demonstrations, which isn't always obvious. But in learning to optimize, demonstrations come from, for example, better solvers or solvers that we can run at training time that might be too expensive to run at test time. But there are other demonstrations that we can collect as well for other applications. And so we're going to talk about basically two types of imitation learning, behavior cloning and one other type, and then I'll briefly mention the full landscape. I'm just this is just to recall the notation. We have state, we have action, we have a policy, and we have dynamics not known to the policy. We have a rollout. So we have this trajectory tau, that's the rollout of a policy in the environment. We also have rollouts from the expert. So those are called expert rollouts. And then we have these notational simplifications of the probability of seeing any given trajectory under this policy, and the probability of ever visiting any given state, so the probability of visiting any given state at any point in time, given a condition on a policy. And let's just skip this one. So now let's talk about behavior cloning, which is the simplest version of imitation learning. And it's literally just a straight up reduction to supervised learning. So we define P star as the distribution of states visited by the expert. And this is averaged across all time steps. And the learning objective is as follows. So given the state action pairs in the rollouts of the expert, so some expert is playing this game and we're recording all the actions taken by this expert, then we want to, so for all the states that are visited by this expert, we want to learn a policy that predicts the action that matches the action taken by the expert in that state. That's the learning objective you see at the bottom. So what are some interpretations? So notice that the generating distribution of the data here has no dependence on the policy that we're learning. The generating distribution is induced by the dynamics of the environment and by the decision-making of the expert. So what does it mean to actually learn this objective function well? It means, given that we've imitated the expert perfectly so far, by minimizing this loss function, we can continue to learn. We can continue to imitate the expert perfectly. More generally, you know, in imitation learning, we care about the distribution induced by our own policy. So, given the states visited by our own policy, that's in the bottom objective. How does the decision making of our policy deviate from the experts for those states? Now, these two objective functions are different because in behavior cloning, we just ignore the fact that we care about distributions induced by our policy. We just say, well, the only data we have where we have demonstrated actions are from the experts, so we're just gonna, you know, do supervised learning on that distribution. Any questions? So limitations of behavior cloning. Suppose that our policy makes a mistake at a certain state. And it decides to veer the steering wheel left at this particular state, which is a bad idea. That is not what the expert did. The new state is not sampled by the expert. The expert has never seen this new state on the right. And so nothing in our training data of demonstrations contains this state. And so behavior cloning, which is, you know, the sort of the default imitation learning algorithm, because it's so simple, cannot handle this very well, because it does a straight up reduction to supervised learning, and it assumes that at test time, the states that we see are sampled from the same distribution as we trained on, which is violated here. So that's what you see in the diagram on below. Behavior cloning makes this assumption on top, whereas in reality we get this circular dependency on this generating new states, just like in reinforcement learning. So I'm not sure the videos will play well, but of course if they don't play well, you can watch the videos on the slides. So this is an expert trajectory. So someone's playing the game, and we're recording the state action pairs. This is work by Stefan Ross, who was a PhD student at Carnegie Mellon, now at Waymo, I believe. Oops. Let's see. So this is behavioral cloning trained on the demonstrations. And then at some point, it makes a mistake because it doesn't imitate the expert perfectly. And then it goes crazy because it's encountering states that it has never seen before during training, and that the expert has never visited during training, and it cannot recover. So when do you use behavioral cloning? Well, the advantages are it's super simple. The disadvantage is that, you know, it has this massive issue with distribution mismatch between training and testing. And so it doesn't know how to correct for its own mistakes because it just has this finite sample of that demonstrations from the expert, and that's all it knows what to do with it. You can use it. You can still use behavioral cloning. One-step deviations are not too bad. So if the expert trajectory somehow cover the state space well enough, then the behavioral cloning isn't too bad. And this may be okay for learning certain types of reactive behaviors. One should not use behavioral cloning when one-step deviations can lead to catastrophic error, which is what we saw in that race car scenario. And also, you know, if you need to do, you know, more looking into the future than learning reactive behaviors. But we're mostly going to focus on the first point, where, you know, how do you deal with this distribution mismatch between these one-step deviations causing catastrophic errors. Okay, so I'm going to talk about the landscape of imitation learning. Mostly just talk about one method and then just briefly mention the others. There's sort of the landscape of imitation learning can be broadly broken down into these three categories, although this is an oversimplification. Behavioral cloning, interactive imitation learning via using direct policy learning, and inverse reinforcement learning. And they can be broken down into sort of these categories where are we directly learning a policy, or are we learning some notion of a Q function or a reward function? That's the first two columns. Do we have access to the environment? So in behavioral cloning, you actually don't need access to the environment. Since you're doing a straight up reduction of supervised learning, you just collect the data once from the environment, from the expert, and you don't need the environment afterwards. The other two approaches that are more sophisticated need access to the environment. Do you need on-demand access to a demonstrator that you can query? And in interactive imitation learning, the answer is yes. In inverse reinforcement, the answer is no. And do you need pre-collected demonstrations? In behavioral cloning and inverse reinforcement learning, the answer is yes, because you're not querying the expert at training time. In interactive imitation learning, you don't actually need demonstration of the expert pre-collected because you're querying the demonstrator at training time. But, you know, oftentimes in practice, you do start with a set of pre-collected demonstrations. And then many other considerations, you know, the choice of imitation loss, you know, how do we characterize the disagreement between the policy's predictions and the demonstration? What happens if this policy, if the demonstrator is highly suboptimal or partial? These are things that sort of motivate connections between imitation learning and reinforcement learning, things that bridge the two, domain transfer, structured domains, and so forth. So this is behavior cloning in a nutshell. We have the key thing here is that the state distribution is the distribution of states visited by the expert, and this works well when the expert's states are close to pi. So you can sort of imitate experts so well that this distribution mismatch is not too bad. Direct policy learning via interactive imitation learning works as follows. We have access to a demonstrator that we can query during training time. So then we roll out, we roll out in the environment and then we collect demonstrations from the expert based off our rollout. So in this state that our policy visited during a rollout, what would the demonstrator would have done? And then we take those demonstrations, we do a reduction to supervised learning, and then we learn a policy, we roll out the environment again, and we repeat. And so every time we do this, we require access to a demonstrator that tells us what they would have done at the states collected by our policy. In some sense, one can think of behavior cloning as a one iteration special case of interactive imitation learning, where we do this cycle once in the very beginning, where we just look at the expert's own rollouts. And the other class is inverse reinforcement learning, where the goal is to learn a reward function such that it explains the expert's behavior. Assuming that the expert is rational under some implicit reward function, the goal is to learn a reward function that explains the expert's behavior. That's why it's called inverse reinforcement learning. So reinforcement learning is given a reward function, learn a policy. Inverse reinforcement learning is given demonstrations from some policy, some expert, learn a reward function that explains the decision making of that policy. But we're not going to really talk about inverse reinforcement learning much because it's less relevant for learning to optimize, at least currently. So direct policy learning, behavior cloning is the simplest example. And one way to think about interactive imitation learning is to, at least from a theoretical standpoint, is via what's a concept called learning reductions. I'm not going to talk about learning reductions much in this lecture, but if you're interested, I refer you to the link below. Learning reductions was largely pioneered by John Langford, who's currently a researcher at Microsoft Research. And you can see many of his other work on learning reductions in that link below. I just want to mention that from a theoretical angle, a lot of this is analyzed via learning reductions. The one-step definition of learning reduction is you take a harder problem and you reduce it to a problem you know how to solve. So for example, you have this harder problem where the generating distribution of states is induced by our own policy. So theta appears in both the objective function in the loss and in the sampling distribution of the expectation. And we'll reduce it to something where theta no longer appears in the generating distribution of the expectation because that's completely generated by the expert policy. And so we've reduced imitation learning to supervised learning. That's what behavior cloning is doing. And one thing that's nice about this one is that, this is literally just, something you can just call really quickly in TensorFlow or PyTorch. And the question that learning reductions seek to answer is, what does learning well on B imply about A? If we learn B really well, what does that imply about A? And so suppose that we have a loss function that makes sense. So if we perfectly imitate the expert, we get zero loss. That's what the top line says. And suppose that this supervised learning reduction, this behavior cloning, where we're just doing supervised learning of the expert data, we get epsilon loss, where epsilon is pretty small. It's like 0.1 or 0.05. Then if we roll out this policy, then the worst case number of mistakes, assuming the length of the trajectory is capital T, is T squared epsilon, which can be pretty bad. If T is 100, this can be pretty bad. Oops. Right. So, if we go into the setting where if we make a mistake in the wrong state, then the error is catastrophic. Then the actual imitation error it can be very, very high, even though the supervised learning of just the expert demonstrations look very, very low. In particular, if you make a mistake at the first time step and it's a catastrophic mistake, then the full imitation error is basically 100%. Any questions about this? Oops. Sorry about that. So the idea behind interactive imitation learning is that we're gonna keep querying the expert as we do learning. So we don't just have the expert just at the beginning; we have the expert over time throughout learning, and hopefully the sequence of generating state distributions converges to the one that our policy to the optimal policy that we can learn. That's the basic idea. So again, this is a pretty strong assumption that we can query the expert at any state. So that you see in the figure on the right, we executed a certain trajectory, that's the blue line, and the expert says that at each of these states, what the expert would have done to behave optimally given this state that we're in. There are ways to relax this assumption, of course, but in the simplest case, this is, the expert is providing feedback on every state of a rollout by the current policy that we've learned so far. And so the algorithm that I'm going to briefly describe is called DAGGER, which stands for dataset aggregation or data aggregation. You can see the links to the paper on the bottom. So in the beginning, we start with the expert, and we collect demonstrations from the expert. And then we have a training data from the state distribution of the trajectories collected by the expert, and we train. So for m equals 1, this is exactly behavioral cloning. For m equals 2, we roll out the policy that we learned from behavioral cloning, pi sub 1, in the environment, and then we ask the expert to give feedback on every state. On every state in the rollout, we ask the expert to say, what would you have done in that state? And then we train on that. That's the third bullet point. And the reason why this algorithm is called dataset aggregation is that it's trained on the union of all the previous demonstrations. So basically at every iteration of this problem, we roll out the current policy. We get a bunch of trajectories. We ask the expert to annotate the trajectories for every state in that trajectory, what the expert would have done in that state, what the optimal action according to the expert would be. And then we take the union of all these demonstrations collected over all the states visited by all the previous learned policies, and we train a new policy on the union of all that data. In other words, we reduce the supervised learning over the union of all the distributions from all previous iterations of the policy and all previous demonstrations. So the intuition is that the way as we do this, the expert is correcting mistakes made by the current policy. So wherever the policy makes a mistake, you get more feedback from the expert saying that particular action is not good, and you can show, and I'm not going to talk about the theory, that this converges to a near optimal policy. This very simple algorithm, and DAGGER is one of the most popular algorithms for imitation learning for learning to optimize. A lot of the methods that we see are built on top of DAGGER. So this is just a summary of the types of imitation learning. I think I'll just move on in the interest of time. So very briefly, just to revisit reinforcement learning, inverse reinforcement learning. The goal is to learn a reward function such that our policy maximizes this reward function. So the policy, so this is basically just Q learning. This can also be thought of as inverse Q learning. So the reward function here is basically like a Q function. We want to learn this reward function such that behaving optimally with respect to this reward function matches the distribution of policies. That's the basic idea. Inverse reinforcement learning is not super popular in learning to optimize, so I'm just going to skip it. And the reason why it's not super popular is that we typically have access to a demonstrator at training time. So for example, we have access to like a more expensive solver at training time that maybe we don't want to run at test time. And there may also be challenges with being able to actually learn a good reward function for decision making. This is the same issue with Q learning. In Q learning, you have to learn a Q function good enough that you can directly use it for decision making. Sort of a similar issue is happening here, and in different applications that may be harder or easier. So in the final 15 minutes or so, I'm going to circle back on some learning to optimize problems that we've already seen in lecture, either in the lecture thus far, or actually problems that we covered in CS 155 that I'm going to revisit in the context of learning to optimize, and then we'll see how imitation learning, reinforcement learning maps to these problems. But any questions about imitation learning? Okay. So the first thing I want to talk about is structure prediction. So structure prediction is a mapping from some structured input space X to a structured output space Y that typically, and making a prediction in a learned model typically requires solving an optimization problem at prediction time. The example that we saw in CS 155 is the Viterbi algorithm for sequence prediction in hidden Markov models. So that is actually a structure prediction problem. It's arguably the simplest structure prediction problem. There are many other structure prediction problems that exist in practice, things from like natural language processing tasks like parsing or protein folding or structure prediction or planning. And there are many, or predicting rankings for recommender systems. There's so many applications of structure prediction. But we're going to stick with sequences because that's what we've already seen in CS 155. So the goal is to learn a decision function. So when we talk about hidden Markov models, we trained this model, which is very restrictive. And we ran Viterbi on this hidden Markov model to be able to predict the optimal sequence. So instead of doing that, suppose that we just learned a policy that makes good local decisions for sequence prediction. So the state is the prefix sequence that we've already predicted so far. And the action is the next token to add to this sequence. That's it. So instead of running Viterbi, we're gonna do this. So, we can do structure prediction basically as imitation learning. The ground truth or the demonstrations are the ground truth sequence labels. And again, we need to deal with distribution shift, what happens if a policy makes a mistake. There are cases where we can do structured prediction as reinforcement learning. In some cases, we just have an objective function without labels. And any labels that we get are suboptimal. And so if we have an objective function, so this is often the case, for example, in things like machine translation, where it's we have this some objective function, and actually optimally solving it can be hard. And we need to sample or explore to find better labels. And so one example of that is this paper called "Learning to Search Better Than Your Teacher." You can see the link below. We can do learning of greedy algorithms. So the example I gave you for learning this sequence prediction to replace HMMs, that's a greedy algorithm, right? It never backtracks, whereas the Viterbi algorithm actually does a little bit of backtracking. But in general, we can just say, look, we're training a policy that's a neural net. It's gonna make pretty accurate predictions, and so it won't need to backtrack. And so let's just do imitation learning or reinforcement learning to learn these greedy policies for structure prediction. For those of you familiar with some modular optimization, some modular optimization is optimized by a greedy algorithm, and so we can actually use imitation learning to imitate the behavior of a greedy algorithm. If you're not familiar with sum-modular optimization, don't worry. This is just this one slide, just for your reference. And what I'm just showing below is just the reduction to supervised learning. So this is basically building on top of Dagger. And sum-modular optimization is a form of structure prediction. So in some sense, in the context of what we've been talking about in this class, structure prediction can be thought of as learning to search. You compile the input description of a structure prediction problem into a search problem. And then you train a policy to effectively navigate this search space. And the expert might be weak. So you might need to do both reinforcement learning and imitation learning, or blending of the two. And thus far, the examples that I've all shown you were we treated the search space as a greedy search space. So pi is we're training a greedy algorithm to make good local decisions without backtracking, such that it does as well as possible. More generally, we could train policies in the context of search problems where we do allow backtracking, such as learning a decision module within the branch and bound framework. And so here we do actually have a reward function. The reward function is, did we find a feasible solution, and how good is the feasible solution? The problem is that this reward function is very sparse. In many of these combinatorial optimization problems, the terminal states where we found a feasible solution might be few and far in between, might be a vanishingly small fraction of the total number of states, which can be exponentially large. And the demonstrations are provided by an existing solver like Gurobi or Cplex, which may be suboptimal. So you have suboptimal experts, and then you have a sparse reward function. And so one of the interesting questions is, you have these, you have like the worst of both worlds. You have suboptimal experts that are expensive to query because they require solving an optimization problem or a solver. And then you have really sparse rewards that's really hard to optimize directly using reinforcement learning. Are there ways to mix between reinforcement learning and imitation learning to sort of use both of these things and to good effect? And we'll talk about this in another lecture later in this class. And one thing I just wanted to circle back on is this algorithm that we talked about in the previous lecture, which is learning a greedy algorithm for combinatorial problems. So now we can just revisit this algorithm, given all the information we've seen today, and we notice that it just specifies a policy class in terms of a graph neural network, and then it does this greedy sequential decision making that we've been talking about so far, where if your policy class or if your local search heuristic is good enough and accurate enough, in many cases it suffices just to learn a greedy policy that never does any backtracking, because your policy class is a deep neural net. And if you don't have access to good demonstrators, we can just sample the reward function of the environment, which is the quality of the solution of this combinatorial optimization problem. And so in this particular paper, they do Q-learning, which we just saw before. It's a slightly more complicated version of Q-learning, but in essence, it's Q-learning. So this gives you a sense of how all these methods tie together to solve these combinatorial optimization problems. Any questions? Okay, just one final thing. We talked about meta learning. We talked about imitation learning. People can do meta imitation learning. This is not super central to this course, but I figured I give it a plug because it just combines two ideas that we've already talked about, where if you want to quickly translate to a new domain with very few demonstrations, you could do this sort of meta imitation learning approach. This is just the basic idea. I'll skip it in the interest of time. So the next few lectures will be guest lectures, two of them by our TAs, and one of them by Brandon Amos. So Brandon is a research scientist at Facebook Research. He did his thesis work on differential optimization, such as OpNet. And so he'll be giving the guest lecture next Tuesday. So the immediate lecture on Thursday is advanced Bayesian optimization techniques. I'll be I'll be giving that lecture. And then the next 3 lectures following next lecture, starting next Tuesday, will be by Brandon, Joe, and Jialin on these topics. And that's the lecture for today.